Hello friends, welcome to this lecture. In this lecture we will start our discussion on linear system and its properties, existing uniqueness and some properties related to linear system. So, first let us see that the system of differential equation are quite useful and widely used in several areas of science and engineering, and there are some common which we have already discussed, that is some problem related to pendulum problem, population models, mixing problem. Mixing means we have tank mixing problem, fluid mixing problem, control problems. These are some of the problems which can be studied using system of first order differential equations. Now, in general we can define the first order differential equation system as follows. So, consider the following system of first order differential equation: dx1 by dt equal to f1 t comma x1 to xn, dx2 upon dt equal to f2 t comma x1 to xn, and so on, dxn upon dt equal to fn t x1 comma xn here. Now, here these fi's are I equal to 1 to n are given functions defined in a region D of n plus 1 dimension Euclidean space, and these xit I from 1 to n are the n unknowns function of an independent variable t. So, our aim is like to find out these xi's such that it satisfy the equation number 1 for given f1, f2 and fn. So, along with most of the time, along with the ordinary differential equation, we often have conditions to be satisfied by the solution at a fixed point, say t equal to t naught, and which can be written like this, that x1 t naught is equal to x1 naught, x2 t naught equal to x2 naught, and so on, xn t naught equal to xn naught. So, equation 1 means the differential equation 1 along with the conditions which is defined at t equal to t naught, most of generally called as initial conditions. So, equation 1 together with the initial condition 2 is known as an initial value problem, and in a layman language, a solution of the initial value problem is a solution x1 to xnt of 1 satisfying the initial condition 2. So, it means that roughly I can say that the solution of the initial value problem is a n unknowns x1 to xn such that it satisfy the equation number 1 along with the condition given in 2, that is x1 t naught equal to x1 naught, x2 t naught equal to x2 naught, and so on. So, now let us consider some example through which we try to understand the concept of system of differential equations. So, consider the following system of linear differential equation: dx1 by dt equal to x1 plus x2 comma x1 0 equal to 1, and dx2 t upon dt equal to x2 comma x2 0 equal to 1 here. So, here it is similar to your problem x1 dash equal to ft x1 comma x2 and x2 dash equal to ft f1 and f2 x1 and x2. So, here your f1 of t comma x1 and x2 is given by x1 plus x2, and f2 t x1 and x2 is given by say x2 here, and initial condition is given at the point 0, that is x1 0 equal to 1 and x2 0 equal to 1. Now, here if you look at this system is defined, and if you look at the second system, that dx2 by dt is equal to x2. So, it means that the function f2 is not depending on the variable x1, and so we can easily solve this system, this linear equation dx2 by dt equal to x2 provided that x2 0 equal to 0, and you can find out that x2 t is equal to constant times e to the power t, and the condition x2 0 equal to 1 will fix the value k, and it is given as e to the power t. So, x2 t is given as e to the power t, and once your x2 t is given to you, you can use the first equation, that is dx1 by dt equal to x1 plus x2, and you can find out the value of x1 also. So, here we can say that x1 dash t is equal to x1 plus x2 is given as et, and x10 equal to 1. If you look at, this is nothing but a linear differential equation, scalar linear differential equation, and you can simplify, you can write it d by dt as e to power minus t x of t is equal to 1. What you can do, you just multiply by e to power minus t, which is the integrating factor of this part, x1 dash t minus x1, and we can simplify, and then you can write this as e to power minus t x of t equal to t plus some constant, let us say called c, and the condition is given that x10 equal to 1. If you use the condition, then it is nothing but 1 equal to c. So, it means that c is fixed now. So, we can simplify this and we can write down that x1 t equal to e to power t times 1 plus t, and x2 t equal to e to power t is a solution of this system of linear differential equation. So, here we can say that the given system of linear differential equation is having a solution x1 t equal to e to power t 1 plus t and x2 t equal to e to power t, and we can call this as that x1 and x2 forms a solution set of the initial value problem given as this. Now, coming to example number 2, which is very important in the sense that it gives you the way that any differential equation of nth order can be reduced to a system of first order differential equation. So, here the differential equation is given as this, that dn by upon dn by dtn equal to f t comma y dash up to yn minus 1, along with the initial condition, that is y t naught equal to y naught, y dash t naught equal to y1, and yn t naught equal to yn minus 1. So, this is the nth order differential equation, and we want to convert this to a system of first order differential equation, and let us see how we can do this. So, for converting it, let us assume some n variables, and these n variables we can say that it we can identify that this is nth order differential equation. So, we have to choose n number of variables, and let us choose n number of variables like x1 t equal to y, x2 t equal to dy by dt, and xn t equal to dn minus 1 dt n minus 1. Now, using the definition of these variables, we can simplify that x1 t is equal to y1 and x2 t equal to dy by dt. So, if we combine this, we can say that x2 t is equal to dx1 by dt. So, first differential equation we can write it as dx1 dt equal to x2, and similarly we can look at x3 t is equal to dy by dt square, and we can simply say that this is nothing but d by dt of dy by dt, and dy by dt is x2. So, we can say that your x3 is x2 dash t. So, we can write dx2 dt equal to x3, and so on. In this way we can say that dxn by dt is equal to f t comma x1 comma x2 and so on. So, it means that here we can write down our equation like x1 dash x2 dash up to xn dash, and this I can write it here as say x2 x3 and so on up to ft x1 comma x2 and so on. So, it means that this is the differential equation, system of first order differential equation, and initial condition also we can find out. So, initial conditions are given as y t naught equal to y naught, y dash t naught equal to y1, and yn t naught equal to yn minus 1. So, since we have assumed that x1 t is equal to y, so we can say that y of t, so we can say that x1 of t naught is equal to y naught. Similarly, we can say that x2 t naught equal to y1 and so on, xn t naught is given as yn minus 1. So, it means that along with the system of differential equation, we can get our initial condition as x1 t naught equal to y naught, x2 t naught equal to y1, and up to xn t naught equal to yn minus 1. So, this is the system of differential equation along with the initial condition defined like this. So, it means that this example gives us the idea that every nth order differential equation, ordinary differential equation, can be reduced to a system of first order differential equation in this way, in the way which we have just discussed. Now, moving on to example 3, and here we consider this system x1 dash equal to x1 minus t x2 plus e to power t, x2 dash equal to t square x1 minus x3, and x3 dash equal to x1 plus x2 minus x3 plus 2 e to power minus t. Now we want to form the system of first order differential equation from this, and here we can say that each system here this is linear in terms of x1 comma x2 and x3. So we can form this equation number 3 as follows: x dash equal to f dx. We can look at the equation number 3 as x dash equal to f dx, where x is defined as a vector x1 comma x2 comma x3, and f dx we can define as x1 minus t x2, t square x1 minus x3, x1 plus x2 minus x3 plus e to power t comma 0 comma 2 e to power minus t. So it means that we can rewrite this equation number 3 as x dash equal to f dx, where x is a vector given like this and f dx is a vector given like this. So it means that this vector, the vector given here, can be further simplified, and you can write down this vector x1 minus t x2 t square x1 minus x3 and x1 plus x2 minus x3 as atx, where at is given as 1 minus t comma 0, t square 0 minus 1 1 1 minus 1, and x is given like this. So it means that this system I can write out equation number 3, I can write down this as x dash equal to atx plus say f of t like this, where f of t is your given by e to power t 0 to e to power minus t. So it means that the system given in as equation number 3 can be reduced to x dash equal to atx plus ft, where ft is given like this and at is defined as follows. And here your x is regarded as column vector, and the system 3, as we have pointed out, is written as x dash equal to atx plus gt, where gt is a given vector e to power t 0 to 2 e to power minus t, and it is also regarded as a column vector. Now if you look at gt is what, basically here gt is a vector valued function. So it means what, that for each t this e to power t gives you a real value and 2 e to power minus t gives you a real value. So it means that for each t gt belongs to R3 cross 1. So it means that for each t gt gives you a vector in 3 cross 1. So gt gives you a 3 cross 1 vector for each t. So in general we can define like this: a vector valued function g equal to gt is a relation that assign each number t in an interval I to a unique vector gt. So it means that it is a map from say an interval which belongs to, so t belongs to I. So it means I can write g as from I to say r n cross 1 here. So for given t you can map to gt, which is denoted as g1t, g2t and so on gn t. So basically here vector valued function g is defined as a map which is a map defined from I to r n cross 1. For given any t, it gives you a vector defined as gt like g1t, g2t and gnt, and we call like its components are the kth component of the vector function g, and we may define the continuity of these vector valued function, continuity, differentiability and integrability of these vector valued function in terms of its component. So we can say that g is continuous, differentiable or integrable on an interval I if each component of g, means g1t, g2t and gnt, has the said property. It means that if g is said to be continuous, if each component is continuous, g is said to be differentiable if each component is differentiable, g is said to be integrable if each component is integrable. Now we can define, if g is differentiable, we can denote the derivative of g by g dash, and it can be given as g1 dash t, g2 dash t and gn dash t. So it means that the property continuity, differentiability and integrability is given in terms of component, and we can find out the derivative of vector valued function g in terms of its component, and it is given by this, that g dash equal to g1 dash t, g2 dash t up to gn dash t. And in a similar way we can define that if g is continuous on interval I, then we denote its integral from a to b by a to b gs ds, and we can define a to b gs ds as basically it is also a is a vector. In the first component it is a to b g1 s ds, a to b g2 s ds, and a to b gn s ds. So it means that integral of g of s ds is basically is integral of its each component. That is how we define the integral of a vector valued function, and most of the time we use this kind of important inequality, that is norm of a to b gs ds is less than or equal to a to b norm of gs ds. Now here this represent the norm of a vector valued function, and here and this we will talk about this norm little bit later, and we will see what kind of function is defined as a norm of the function. Now to prove this inequality, we can simply write the norm of a to b gs ds, and here norm we are taking like this, that norm of y is nothing but absolute sum of its component, that is norm of y is given as I equal to 1 to n modulus of yi. Now here it is simply modulus, and here this represent the norm of y, and to differentiate between the modulus and norm, many a times we use this notation, that is this like this. So here when we consider the vector valued function, this is denoting this denotes the norm of vector valued function, and when we talk about the component, then this represent the modulus of or absolute value of its component. So we can refine norm of a to b gs ds equal to, as we have already defined that here norm is given at the absolute sum of its component. So we can write down the modulus of a to b g1 s ds plus modulus of a to b g2 s plus so on a to b modulus of a to b gn s ds. Now this can be written as this can be bounded by less than or equal to a to b modulus of g1 s ds, and similarly this can be this is bounded by a to b modulus of gn s ds. Now if we can simply write this as a to b, and we can write g1 s plus g2 s plus and so on gn s ds, and if you look at this is nothing but norm of g here. So we can write this a to b norm of gs ds. So I can write it like this. So here to prove this inequality, we are using the definition following definition of norm, that norm of y is summation I equal to 1 to n modulus of yi, right. Now here I am assuming that yi's are real valued function. Now if it is complex valued function, then this modulus is supposed to be the modulus of yit, that is here if yi are complex, then I can write this as ai plus ibi, then modulus of yi is nothing but the under root ai square plus bi square. So here right now I am assuming that yi are real valued function, that is why I am calling it as modulus function, otherwise it will give you the absolute value. So in case of complex, I can consider this modulus of yi as under root ai square plus bi square. So it means that this property is very useful and we will use in a later slides. Now we define what we mean by solution of the system. So for that we consider the system x dash equal to f dx, where the vector valued function f is defined in some n plus 1 dimension region D in t comma x1 comma x2 comma xn space, and we try to define what do you mean by the solution of the system 5. So here we define what we mean by solution of the system. For that we consider the system x dash equal to ftx. Here x is a n x1 to xn and it is a vector in R n cross 1, and f is a function, vector valued function defined in n plus 1 dimension region D in t comma x1 comma x2 comma xn space. Now what do you mean by solution of the system? To find out a solution of the system 5, we need to find out a real interval I. First of all, we need to find out an interval I in which this vector function x is defined, and defined in a way such that x dash t exists for each t in I. Second, the point t comma x t lies in domain D, where we are talking all this thing for each t on I. So for each t, the tuple t comma x t will lie in domain D. Third, that x dash t equal to f t comma x t is satisfied. So first thing is that derivative exists for all t in that interval. Second, for each t, your t comma x t will lie in your domain, and third is that derivative exists and it is equal to the value of f t comma x t for every t on this interval I. If it is happening, we call the system the vector valued function x as a solution of the system 5. And to solve an initial value problem for the system with the initial condition x t naught equal to eta. So if along with this equation number 5, if we have initial condition given as x t naught equal to eta, here eta is also a vector in n cross 1. So eta is also a vector of size n cross 1, and we want to find out a solution of x dash equal to ftx with the initial condition that x t naught equal to eta, where t naught and eta is a point in domain D. We need to find out a solution x of 5, means this system passing through the point t naught comma eta of D, that is x of t naught is equal to eta. So solution of the system is having these three properties, and solution of the initial value problem is in additional property that x of t naught is equal to eta. It means that it is passing through the point t naught comma eta. Now for once we know the notation of solution, what do you mean by solution, then our first thing to consider is the existence of solution. So as you remember that we have discussed the existence and uniqueness theorem in a scalar valued case, that is when we have x dash equal to f t comma x, where x is a scalar valued function. Now in a similar way we can define the existence and uniqueness theorem for vector valued function also. So let us consider the following theorem. Let f be a vector function with n components defined in a region D of n plus 1 dimension Euclidean space, and let the vector f and diver f by diver x k, where k is running from 1 to n, be continuous in a domain D. So first thing is that we have a vector valued function f which is defined in a region D of n plus 1 dimension Euclidean space, and assume that f and its partial derivative up to nth order are continuous in that domain D. Then given any point t naught comma eta in D, they exist a unique solution x of the system x dash equal to ftx, which satisfy the initial condition x t naught equal to eta, and the solution x exists on any interval I containing t naught for which the point t comma x t with t in I lie in D. And if you remember in scalar valued function, this theorem is a local existence theorem. So it means that here the solution will define in a neighborhood, a small neighborhood of t naught comma eta. So that is why we are saying that solution will exist in an interval I containing t naught for which this point t comma x t where t is in I lie in domain D. Furthermore, the solution x which we obtained is a continuous solution corresponding to t. So it means that first thing is that solution exists in a neighborhood around t naught, and the obtained solution is continuous, is a continuous function satisfying the equation number 6. Now, if this domain D which we are talking about is the entire T x space, then from this theorem we can say that it follows that every solution exists as long as its norm remains finite. So, it means that the if this we are talking about this domain right now. Now, if this D domain D happens to be the entire space, then for any point we can find out a domain D and our solution exists in that in an interval I, which for which the point t and xt lies lying in the domain D. Now, if D is the entire space, then we can say that the solution exists using the theorem 1 as long as the norm of that solution remains finite, right. So, it means that this solution will exist for all t for which the solution is bounded solution. So, solution is a bounded solution. So, this gives you that if domain region D or domain D is the entire space, then we have to look at the region in which your solution is bounded. Solution is bounded means the norm of the solution is bounded, and we say that solution exists for all t for which your norm of xt is bounded. So, let us consider example based on whatever we have discussed. So, consider the example 2, say consider the scalar valued function scalar differential function x dash equal to alpha x for some constant alpha, and here we can check that f t x is alpha of x and del f by del x t comma x is alpha. So, it means that here x dash equal to f t comma x, and this f is continuous because it is alpha x, it is continuous for all x, and the derivative of f with respect to x which is given as alpha, alpha is a constant value. So, it is also continuous for all for the entire space. No, so here we can say that both f and del f by del x are continuous in the whole T x space. So, by the above theorem there is a unique solution phi of x dash equal to alpha x through every point t naught x naught in the plane. So, it means that given any point t naught x naught, the solution of the this problem x dash equal to alpha x and x of t naught equal to x naught. So, it means that for every initial condition solution of this problem exists. Now, we can also verify that your solution phi t is given as x naught exponential of alpha t minus t naught. That is not very difficult to obtain. You can find out the solution using separation and variable method, and we can say that this is one solution of the initial value problem, and since it satisfies the condition of existence and uniqueness theorem. So, we say that this is the solution of the initial value problem, that therefore, we can say that phi t equal to x naught exponential of alpha t minus t naught is the only solution which we are discussing. Now, we say that we can find out the norm of modulus value of phi t, and you can check that it is given as modulus of x naught into exponential of alpha t minus t naught, and it, if you look at this, is always finite for all finite t such that t comma phi t belongs to the t x space, and here t is lying between minus infinity to infinity. So, it means that this solution phi exists for all t between minus infinity to infinity. So, here since this condition that f and partial derivative of f exists for all t comma x. So, we can say that solution will exist for all t comma x for which norm of phi t is bounded, and you can see that here the norm of phi t is always bounded for all finite t. So, it means that solution of this problem exists for all t. Now, looking at next example, and here also we want to discuss the problem of existence and uniqueness, and consider the system x1 dash equal to t x2 plus x3, x2 dash equal to cos t x1 plus t square x3, x3 dash equal to x1 minus x2, and we can write down this system as x dash equal to f t comma x with x equal to x1 x2 x3, and f t x is equal to t x2 plus x3 cos t x1 plus t square x3 and x1 minus x2. So, here if you look at f t x is continuous, if you look at here this each component is continuous basically. So, t x 2 plus x 3 is continuous, cos of t x 1 plus t square x 3 is continuous, x 1 minus x 2 is continuous. So, each component is continuous. So, we can say that f is continuous for all t such that modulus of t is less than infinity, and for all x such that modulus of x is less than infinity. Now, look at the partial derivative of f. So, partial derivative of f with respect to x 1 is 0 cos t. So, 0 cos t and 1. So, that you can easily verify. You look at del f by del x 1 means here we can write del f 1 by del x 1, del f 2 del x 1 and del f 3 del x 1. So, here the derivative means this. So, del f 1 by del x 1 is basically there is no component of x 1. So, you can say del f 1 by del x 1 is 0, and here it is cos of t and here it is 1. So, similarly we can write down del f by del x 1 as 0 cos t 1, and similarly we can find out del f by del x 2, that is this is t 0 minus 1, and del f by del x 3 is equal to 1 t square and 0. So, we can say that the partial derivative corresponding to x 1 and x 2 x 1 x 2 and x 3 are also continuous for all t such that modulus of t is less than infinity, and for all modulus all x such that mod of x is less than infinity. So, it means that here that f is continuous and del f partial derivative is also continuous for all for the entire 4 dimensional space, that is t comma x 1 comma x 2 comma x 3 space, and through any point t naught comma eta there passes a unique solution phi existing on some interval containing t naught. So, it means that here your solution will exist for which passes through a given point t naught comma eta and containing the initial condition t naught. This is regarding this example number 3. So, we have discussed the existence and uniqueness theorem for some system x dash equal to f t x, and we have seen that solution exists provided your in an interval I such that your f is continuous and partial derivative of f is continuous in that region, and if that region happens to be the entire space, then solution will remain solution will exist for all say t such that norm of that solution is remains bounded, and we have seen some 2 example based on that. Now, let us move to a particular form of f t x such that f t x is linear in terms of x. So, now consider the concept like linear system. So, in system 1, that is x dash equal to f t comma x, if the function f 1 to f n, where f is given as f 1 to say f n, if these function f 1 to f n are linear with respect to dependent variable x 1 to x n, then the system of equation is said to be a linear system. So, it means that if we have system like this x dash equal to f t x, and if f is linear corresponding to x, then we say this system as a linear system. What do you mean by that f is linear in terms of x? So, here you please recall the condition that f t c 1 x 1 plus c 2 x 2, if we can write this as c 1 f t comma x 1 plus c 2 f t comma x 2, if f satisfy this condition, then we say that f is a linear function corresponding to the dependent variable x. So, we say that if f satisfy the following condition, then we call the system of equations as a linear system of equation, and the system which is not linear we call that system as a non-linear system. And we can check that the most general system of n first order linear equation has the following form, that is dx1 by dt equal to a11 t x1 plus a12 t x2 plus so on a1 n t xn plus f1 t, and similarly the nth equation dxn by dt equal to an1 t x1 plus an2 t x2 and ann t xn plus fn t. So, here we can write that this is the most general system of n first order linear differential equation, and it is given by equation number 7 here. Now, if in the system 7 if all these right hand side f1 t and fn t are say 0 function, then we call the system 7 as a homogeneous system. So, it means that the functions which are not involving any dependent variable and it is independent, it is a function of independent variable t such that this so this if these functions are 0 for all t, then we call our linear system as a homogeneous linear system, and a system is said to be non-homogeneous system if it is not a homogeneous system. So, it means that if these functions f1 to fn's are not identically 0, it means that they exist one function which are say non-zero for at least few values of t, then we call this system 7 as a non-homogeneous system of differential equation. Now, we can find out the compact notation of equation number 7, and for that notation let us assume that A to be a n cross n matrix with the element aij aisj and let f t and x be a vectors with components f1 to fn and x1 to xn. Then we can write down the equation number 7 as follows: dx by dt equal to a t x plus f of t, where a t is given as a11 t, a12 t up to a1 n t and so on, and x is a vector defined as x1 comma x2 comma xn, and f t is a vector having component f1 to fn. Moreover, if x1 to xn t satisfy some initial condition given at a fixed point say t naught, then x1 t naught equal to x1 0 and xn t naught equal to xn 0, then x t satisfy the following initial value problem. So, along with the differential equation, if we have x t satisfy the initial condition, then we can say that x t satisfy the following initial value problem, that is dx by dt equal to a t x plus f of t such that x comma t naught equal to x naught, where x naught is defined as x1 0 to xn 0 and f t is given as the vector valued function f1 to fn. Now, so it means that now we from now onward we use compact notation to discuss the linear system of differential equation. Now, if the coefficient matrix, that is A t, is ideally equal to A, it means that A t is not a function of t, it means that its components are constant constant values, then we can say that if A is a constant matrix, then the system 8 is called a autonomous system of linear equation, otherwise the system is called a non-autonomous system of linear equation. So, it means that here if we look at the coefficients here, if all the coefficients are independent of t, it means just a constant value constant value, some real constant, then your system x dash equal to a x plus f is given is known as autonomous system, otherwise it is known as non-autonomous system. So, this is an example of non-autonomous system, and the system x dash equal to a x is said to be an autonomous system of linear equations. Now, let us discuss one particular case of linear system, that is linear homogeneous system, for which consider the linear system of differential equation dx by dt equal to a t x plus f t, where x is given as x1 to xn, a t is given as a I j t and f t is given as f1 to fn. Now, if you look at this f t, if this f t is non-zero, then a non-zero vector valued function, then we call it a non-homogeneous system, and if f t is ideally equal to 0 for all t, then we call this as a linear homogeneous system. So, we in this slide we are assuming that f t is ideally equal to 0 function. So, it means that to initiate the study of linear homogeneous equation, that is there is no external force f t in equation 9, that is we are assuming that this f t is ideally equal to 0 function for all t belongs to that interval I. So, it means that to initiate the study of linear homogeneous equation, we first make sure that the system has a solution. So, first thing is that system has a solution, and then we try to find out that what are the type of solution and how we can find out the properties of solutions of the homogeneous equation. So, first we state the existence and uniqueness theorem without any proof, and the proof of the theorem can be given in a similar manner as we did in the proof of the Picard's theorem. If you remember the scalar valued function x is equal to f t x, and under some condition on f, that is if f satisfy the ellipsis condition, or we can say that f and f partial derivative of f are say continuous, then we can find out that this system this equation has a solution, and that solution is unique in some neighborhood of initial point, that is t naught. So, the only change in the case of vector valued system of linear equation and scalar valued system of linear equation is the say notation of modulus function. So, in the scalar valued function, this modulus represent the absolute difference or absolute difference between the points, but now here this norm this modulus is represented by norm of the corresponding norm. So, here we can restate this theorem, existence and uniqueness theorem. The only change we are going to consider is the change in terms of distance function, that is modulus function. So, here in place of modulus we are going to use the norm function. So, the only noticeable change is the change of modulus function with a suitable norm function, and we may define a norm of a matrix A denoted by norm of A, and in it can be defined in several ways, and all the norms are equivalent to each other. And there is a property of a finite dimensional vector space that whatever norm you are going to define, they are going to be equivalent norm. Equivalent means it is not the same norm, but the qualitative properties is same whatever norm you will choose. Okay. So, this we are going to discuss in next lecture. So, for this lecture we will stop, and we will discuss in next we will continue our study in next lecture. Thank you very much for listening us. Thank you.